Good afternoon, everybody. How's it going? What's freaking you out at the beginning of quarter? Yeah, what is freaking you out? Wait lists. All right. Well, in regards to wait list in this class, it's one of the large COGS classes, so if you've been in one of my classes before, you've heard me say, COGS advising, not me, right? COGS advising is in charge of the wait list. I told them how many people I will take in total, and I also told them, and if you give me an extra TA, I will take another set. I don't have a new TA yet. So, in terms of the wait list, if you are a COGS ML specialization senior, you will have priority. Okay, you'll be the first person off the list or one of the first people off the list. If you're not a cognitive science ML specialization senior, you'll be further back, and the numbers are only approximate. I don't really know how many people to expect to drop this class. It's the first time I've taught it, so I don't know how many people are going to drop and how many are going to be open slots. I do expect some. I just don't know. So if you have special circumstances or worries, talk kindly to COGS advising, because you're one of like 500 people who are asking them the same question. Okay. What else is stressing you out besides wait lists? Nothing? Yeah?
Are we going to have discussion this week, or is it going to start next week?
Great question. Discussion this week, yes. So on Friday, please do go to your discussion sections. So I've been chatting with the TAs, and we are proposing a system to make it really convenient for you to go to discussion section. Come whenever you want. You don't have to go at your appointed time. We're going to run discussion section the same way I'm running lecture. There is going to be a short 15-minute-ish video on YouTube that you can watch at any time. And it's going to kind of give you review of what we're talking about this week and give you the right kinds of mindset to start the notebook. The notebook for each discussion section will be available on GitHub. You can clone it. It is going to be a self-paced thing. It's going to be not for points. It's purely for your practice, right? It's going to be walking you through all the topics we're working on in the current week. It's going to be doing both the theoretical stuff and the programming stuff. And it's going to be like, there's going to be like a little multiple choice Quizlet, and it will tell you what the right answers are and whether your choice was right. So you can learn for yourself. There'll be automatic grading, and will tell you whether your program did what it was supposed to do. But it's just going to be you doing it yourself. So that's why you can either choose not to show up at section at all. I don't recommend. Or just watch the video on your own and come to section and get face-to-face help at any time, right? Like just being in the room with other people working on it, you can all talk to each other as well as the TAs. You can kind of figure stuff out as a group. It's perfectly fine. Help each other study, figure things out, whatever. So that's why there's no fixed times. Of course, as usual in my classes, you don't even have to go, but I do think it's a great opportunity to be in an environment where you guys can collaborate together and work out stuff. Sound good? If you like this system, let me know. If you don't like this system, let me know. You can either, if you want to talk to me personally, that would be great. If you feel like that's a little bit difficult for you as a conversation, just a reminder, we have our anonymous course feedback form, right? That you can leave me suggestions or your opinions. Okay, any other kinds of logistical sorts of questions? I want to remind you that there is a practice assignment to get you used to using AutoGrade or GradeScope. You can do that. No points, just to get the system going. There is the pre-course survey and the quote-unquote syllabus quiz. Both of these are extra credit items. If you are a financial aid student, you probably want to fill out the #FinAid survey, right? You're probably familiar at this point with the certifying the beginning of academic activity kind of BS that we have to do nowadays. And do not come to class on Monday. Monday is a federal holiday, Martin Luther King Day, okay? So those are the logistics items to keep in mind. How about we do some probability and stats, huh? Let me get this stuff going. So I know at least one person asked on CampusWire, can I get the PDFs for the pre-lecture? Yes, it's attached to these PDFs, which went up on the repo like an hour ago. So you can have both these PDFs for class and the pre-lecture. So, I know you all know probability, but let's review the important aspects that we all need to know. We got 2 dice. We're rolling dice 1 and dice 2. We can represent the outcomes as a table, as an outcome table, right? So if I roll on dice 1, I roll a 2. And on dice 2, I also roll a 2. That's that outcome, right? And if I roll a 4 and a 2, that's like that. Okay, I think everybody gets that idea. This is the probability space, or the sample space. And if I want to be all fancy, I might write the idea of the sample space as a Greek letter. That's my attempt at drawing an omega. I apologize to anybody Greek in the audience. Okay, so this is the sample space, omega. And we can represent it this way as an outcome table. Okay, I ask you, the audience, what is the probability that I roll a particular number, a set of numbers, like for instance, snake eyes? 1 out of 36. And why is it 1 out of 36? How can I know that from my outcome table? Yeah?
Because the probability of rolling a number on each die is independent of each other, and there's 6 options for each one.
Okay. So that's an argument from statistical independence, which is true. But I want an even more basic version of that. Like, you don't even have to know how dice work. Yeah? You got it. There are, in fact, 36 squares in our sample space, right? ... 36. And only one of them has the outcome in yellow there, right? So you're right, and I wanted the simpler version of that. Okay, so getting rid of all these things off here. So the probability of rolling one of these particular outcomes is 1 out of 36. Okay, what's the probability that just one of these dice rolls a 1? Anybody want to tell me? 1 out of 6. And when you look at the outcome table, that's all this stuff, which takes up 6 out of 36 squares. You can simplify 6 out of 36 to 1 out of 6. All good? Okay. All right, So, oh, whoops, I forgot to write our answer there. And likewise, we could also do a column, right? It's the same answer. I'm not even going to ask you to tell me, but I just want to show you, you can get what's called marginal probabilities, right? Like if you were watching the pre-lecture, you can see the probability of just one of these outcomes, not both. That's a marginal probability, and you can do the outcome table thing and see what the probability is. Okay. So 1 out of 6, 1 out of 6. What's my next thing? Ooh. What's the probability of both x being equal to 3 and y being greater than 3? Sorry, I couldn't hear. 1/12. Okay, so let's work it out here. So x equal to 3 is this column, and y greater than 3 is here. That's 3 blocks out of 36, which can be simplified to a whole. Okay. These things here that we've been talking about, these are joint probabilities. The probability of two things happening at the same time, right? That's our terminology. We talked about it in the pre-lecture in greater detail. Okay, this is a conditional probability. Given that y has already been rolled and it is 1. Oh shoot, I did myself a dirty here by having to go backwards. Okay, 1/6, 1/12. All right, given that y is 1, yeah? So we know that we're in this row. What is the probability that x equals 1? 1/6. And I want to be very clear, okay? The whole table doesn't matter anymore. We are conditioned on the fact that y is equal to 1 already. So only these 6 squares matter. The rest of the table gets thrown away. And now we're only at 1/6 of the remaining stuff, right? Okay, so that's 1 out of 6. Okay, given that y is greater than 3, that is, we're in this zone, what is the probability that x is equal to 3? Three out of 6 times 3, which is 3 out of 18. Again, we only care about this part of the table now. Okay? Conditional probability. Given that something has happened, what's the probability of the first item in the conditional probability? Okay. Anybody notice something weird and unusual about this conditional probability versus, say, this probability, this marginal one? Do, 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 do. They're the same. Why are they the same? Because they're statistically independent. Only in the case that the random variables are statistically independent could we possibly end up in a world where these two things have the same answer. That is, in fact, the definition of statistical independence. Okay, so I'm going to skip the last one just for the sake of I'm done with this. So, more statistical fun. Here we have our pizza. It's got some slices with pepperoni, some slices with mushrooms. What's the probability of pepperoni? 1/2. All right, what's the probability of mushroom? Also 1/2. Why is my slideshow not working now suddenly? All my stuff's all messed up. All right, whatever. I messed up my slides. You've already seen the joke. Because what's the probability of pepperoni and mushroom? 1/4. Right? What's the probability of pepperoni given mushroom has already occurred? 1/2. And probability of mushroom given pepperoni is likewise 1/2. Right? This is because in this pizza, the two toppings are statistically independent. In general, it is not the case that the conditional probability matches the marginal, but it is when we are statistically independent. Okay, so we can make our lives more complicated, right? Let's see if my slide animations are correct on this one. So in this case, the pepperoni is going to be, five out of 8, right? Is that what I did? Yeah. Okay, good. Probability of mushroom is 1/2, or 4 out of 8. And the probability of pineapple is 3 out of 8. Right? Everybody caught up? Seem good? Make sense? Anybody got questions? Okay, let's get crazy. Given pepperoni, what is the probability of both pineapple and mushroom? 1/3. Great. And if you didn't understand how we got that, let me just note for you there are 3. Nope, sorry, my bad. Wait. Given pepperoni, sorry, there's 5 pieces of pepperoni. Not 1/3. Somebody yelled 1/3 at me, and I said yes. Okay. Given pepperoni, there are 5 slices of pepperoni. So now we don't care about these slices. They're done. Right? We're only starting from pepperoni slices. How many slices have both pineapple and mushroom? 1. So 1 out of 5. Okay? All right. So again, I did myself dirty by doing my slide notations in the wrong order, but okay. So given pineapple and mushroom, there's 2 of those. What's the probability of pepperoni? 1/2. Okay. Note, the conditionals no longer match the marginals. Right? This is not statistically independent pizza. Okay, everybody cool? Understand the concepts involved? Want to ask a question at this point? Okay. I'm sure that you'll return to this. So, where we're at. We know that we can look at these conditionals as the concept of, hey, given that we're starting from that thing on the right-hand side of the conditional, the B, right? What is the probability of A? That is just like the outcome table. Because it's going to turn out that all we can do is we can count up the stuff that is in the intersection, right? And divide it by the entire circle. Right? The probability of A given B, well, it's where the A circle then overlaps with the B circle. So it's this intersection, right? And so that's this. how much of the outcome sample space, what proportion of the space is the and over the whole of B. That's what a conditional probability is. Okay, the funny thing is that you can get to this intersection either starting with the B, or I can have a Wi-Fi dropout. Come on, baby. I don't love you here. You can actually do this. I hate Wi-Fi. All right, so you can start with the B and get the intersection, or you can start with the A and get the intersection. Either way, you get to the same intersection. You can define probability of A and B, or probability of B and A. Either way, you're talking about the same chunk. So these are the same thing. So you can set them equal to each other on the right-hand sides of these equations. And then you can do a little bit more math, a little bit of algebra, and you end up with the famous Bayes' theorem. What is the point of Bayes' theorem? Well, it enables us to start with a conditional probability conditioned on A and get to the flip, get to something conditioned on B. This is very useful in a lot of different ways. We're going to talk about it here in the next couple of slides. You've met the man, I'm sure. It's a kind of cool bit of science history. He's one of those scientists who just did work and nobody knew, and after he died, somebody else went through his papers and said, "Oh my God, you're a genius!" And now we all know this obscure, nobody knew him when he was alive, 18th century pastor. Okay. Carriage return line feed. Ready? I'm going to have to remind you of something else before we go on with Bayes' theorem. Oh, my Wi-Fi. There we go. We have to think about the idea of different kinds of errors for 1 second. When we have on the top here what we predict to have happen, right? This is what our machine learning system is predicting. And here we have what actually happened, okay? In a two-class situation, like for instance a pregnancy test, you are pregnant or you are not. If your pregnancy test says you're pregnant and you really are pregnant, that's a true positive. If your pregnancy test gives you the all clear and you really are, that's true negative. But then we can have two kinds of errors. The false positive error, where the person is not pregnant, but we tell them they are. Okay? False positive test result. Or the false negative error, where somebody is pregnant, but we tell them they're not. Two different ways for your test to fail. False positive result or a false negative result, where positive means the test says you're pregnant. Okay? So I'm sure that we've covered this in 108 or 118A, but I know that for a lot of people that just doesn't quite grasp a hold. Okay, let's use this concept and Bayes together to see the power of a Bayesian approach to probability. You've seen this probably as well. So let's talk about a cancer test, not a pregnancy test. The thing is that cancer is pretty rare. If you just go down the street and poll a bunch of people, it will be a relatively small number of them who are currently cancerous. So we can say that the prior probability of cancer is low. It's something like 0.1%, or 1 out of 1,000. Okay, now we have a new cancer test, a machine learning system we're testing, right? And it gives false positive results only 2% of the time. 2 out of 100 people does this thing actually say you have cancer when you don't. Okay, The same test also has a false negative rate of 10%. 10% of cancer patients get told they're healthy. So what happens when we run this test on 10,000 individuals? Well, we know from here that we expect that only 10 of those 10,000 are going to be actually cancerous. The other 9,990 are going to be healthy. Okay. Now we can use our false negative rate here on cancer, right? Is that what I did first? Come on, slides. Okay. So here is Bayes' rule. The probability of cancer is our prior probability. We know that to be 1 out of 1,000. Okay? The probability of a testing positive, given that you do actually have cancer, well, we can work that out to be 9 out of 10, because we have that 1 out of 10 rate of the false negative. 10% false negative is 1 out of 10. So subtract that 10%, that means we got a 90% true positive. Okay? So we can plug those numbers in to our system. Oh God, I thought I removed all this stupid animation. Oh, I am so sorry. I did it on most of the slides, but apparently not on this one. Okay. So we can also get that denominator, right? The possibility of the test itself being positive just from the data here, right? If we add up this column, we get to 209, and we knew the 10,000, so you can do that and get to 0.02 as our probability of a positive test at all. So just do the math. 0.9 times 0.001 divided by 0.02 is 0.045. What does that mean? Given that there was a positive test, the probability that the person actually has cancer is less than 5%. 95% of people that get told by the test they're cancerous are actually healthy. This is not maybe what you expected when you saw numbers of error rates that were in the region of 5% or 10%. Right? But the truth table and Bayes show you that even though it looks like the individual test is not bad, the fact that there are so many more healthy people than there are cancerous people means that they far outweigh, and you can see it right here, the test positive 200, the test positive and cancerous 9, right? 9 out of 209 is also another way to get to this 0.045. So this is an application of Bayes' probability. So let me introduce a slightly different form of Bayes. It's the same idea where we start with conditioning on the hypothesis and then turn it into conditioned on the data, right? H here stands for a hypothesis we're holding. And D stands for a data set that we're trying to use to see if the hypothesis is true. So we can start with a belief and change our beliefs according to the evidence we gather. This is like doing science, right? We're accumulating evidence about our beliefs and modifying our beliefs according to the evidence. So again, probability of H sub I is our prior probability about what we think of this hypothesis. What's a prior probability? Anybody got some ideas about what a prior means? Yeah?
Is it like before experimentation or data collection?
Before experimentation, yes, that is absolutely a prior probability. How do we know what our prior probability is? We had an example just now. Yeah? Yeah, so for instance, if you have previous data, previous experiments, or some sort of survey that says 1 out of 1,000 people have cancer, that is the basis for our prior probability last time. Probability cancer was 0.1%, 1 out of 1,000, right? We knew that from some sort of experiment or survey or something. Is having prior data from previous things, the only way to get a prior? Anybody got some Bayesian experience want to share with us what an alternative might be? Yeah?
Maybe like an experiment, you have like a control subject, an experiment subject.
Okay, so you're going to propose when you're doing an experiment, you might look at your controls as some sort of baseline. That's a reasonable framework. That can happen in some circumstances. I thought there was another hand. Yeah?
Maybe some sort of like kind of like educated guess.
An educated guess.
Like a null hypothesis or something like that.
For instance, like a null hypothesis. Your priors can literally be what I think. Ideally, what I think is based on something. It could be based on opinion or vague eyeball sort of guessing, or based on an idea like I want to do some sort of null hypothesis testing, and what would a null hypothesis prior be in this situation? So this is very interesting. The idea of Bayesian statistics opens us up to opinion. Okay? It does let us put in our beliefs or whatever framework we're using to think into the system. And one of the neat things about Bayes is that it forces us to do this. The dirty secret of statistics is that every bit of statistics actually does include people's beliefs and assumptions. But they were implicit in the system, in how we did statistics, and some really fine little things about your methods that your beliefs and prejudices can come out in the system. But a Bayesian system forces us to explicitly write down what our beliefs are in the form of a prior and justify them. Yeah?
So if your prior hypothesis could literally just be eyeballing something, does that mean using this formula there's not necessarily a concrete answer to certain probability problems?
That is true. How you form your prior will change your final result. One of the other cool things about Bayes is that this can be an iterative process. We can start with a dumbass prior, accumulate some evidence in experiment 1. We get a new answer on the left-hand side. We can do experiment number 2 using this as our new prior, and then do that again for experiment 3, and so on, and get better and better over time.
If P of HI given D is supposed to be like kind of the new improved hypothesis,
Yep.
would that be kind of used in like statistical tests and stuff to like see if something really good probability.
So, kind of, sort of. Whoops, I went too far. Come on. Oh, I hate this. I hate the Wi-Fi in here. It's so bad. So, there we go. That's the part I wanted to get to. This is what you're saying. So, one important thing to note. What's the denominator here? over all possible hypotheses that I want to consider. It's the same as the numerator, right? Just sum it over all the possible hypotheses I want to consider. So what you actually get out of this is, of all the possible hypotheses, how much of my belief in this particular hypothesis in the numerator should I assign after updating from the new evidence, right? This is a ratio. This down here is a normalization constant. And among all the hypotheses, I'm going to get something less than 1 in the total ratio for each hypothesis. The hypothesis that is the most likely out of all the hypotheses will be the biggest number, right? Does that make sense? And so this is not null hypothesis statistical testing. This is, I've got 3 or 4 hypotheses. One of them is the most probable under this data. Okay? And I can even look at the ratio between 2 hypotheses and see how much better hypothesis 1 is than hypothesis 2. So it's a different framework than null hypothesis testing. But yeah, kind of like that. You can use it that way. Yep.
What's the difference between a potential hypothesis and a potential outcome?
I'm not sure I know what you're saying. So when you say outcome, you mean like something like our dice. Like what's the sample space? And I would say what a hypothesis is something like what's on my next couple of slides, which is I've got a bunch of rolls of the dice. Are my dice fair? Are they even, right? I can test, would I expect to get rolls of the dice like this many snake eyes if my dice were proper 1 out of 6 dice, right? That's a hypothesis I can test. Yeah.
So to clarify, this is testing, or the outcome of this formula is the probability that H sub I is a good hypothesis
Yeah.
to all the others?
Given the data we've observed, right?
Okay.
We start with an initial belief. That's the prior probability on the hypothesis. We've gathered some data. But we also know what's the probability that this hypothesis generates that data. Again, think of the fair dice, right? If my data includes just a ton of snake eyes rolls, that would be very weird for 1 out of 6 dice, right? So I know from the distributions what is the likelihood of observing out of like 10 rolls of the dice 6 snake eyes. It's very, very low. It's 1 out of 36 times 6, right? It's a very tiny number, highly unlikely. That's the probability of the data given the hypothesis of a fair die, right? So this is something we start with. This is something we can calculate given the data. And we can normalize that across 2 hypotheses, fair dice, or a dice that's biased towards the 1 in some particular ratio that you want to pick. Okay? And we can compare those hypotheses. Make sense? We're going to do it explicitly in about 2 slides. Okay? All right. So this is the joke we always use in a Bayes class. If you're not a fan of the XKCD comic, I highly recommend you check it out from time to time because it's got some good science jokes. So here's the system. We've got a detector, a neutrino detector. If you're not familiar with astrophysics, neutrinos are particles that are so massless, they go right through solid objects and come out the other side. But you can, on very rare occasions, build a giant tank of heavy water and catch a neutrino streaking across the water as it interacts with very low percentage with the water. The sun emits gajillions of neutrinos all the time, and they mostly pass right through us and we don't even notice. So when you are on the dark side of the Earth, away from the sun, you can't see the sun. But the neutrinos are passing right through the Earth and into your neutrino detector. Now, if the sun goes supernova, it's going to throw out not gajillions, but quintillions, or some giant number that I can't even say. And so you're going to get a big spike in neutrinos. So our neutrino detector could tell us when we're at nighttime that the sun exploded, if the sun exploded. But our neutrino detector is a liar with probability 1 out of 36. So if you're not using prior belief, if you're just saying, oh, 1 out of 36 chance that it lied to me when the detector says the sun just went supernova, I guess I have to accept that p less than 0.05 because 1 out of 36 is a number smaller than 0.05, right? Classic hypothesis test. The sun just exploded. But if you incorporate your prior beliefs, well, you're the right-hand statistician, right? Okay. Any joke that has to be explained this far is not funny. I get it. It's okay. But I want you to absorb the idea that prior beliefs do matter. Okay. So instead of dice, let's use coins. A fair coin should be 50-50. If we do a long sequence of flips, then we should expect to see something close to 50-50. So we're going to flip our coin 50 times. And let's say that the situation we're in is we're trying to do quality control on coins or something like that. And we know most coins coming off the assembly line are good coins, but every once in a while we get a slightly biased coin. And on average, that bias is a particular value. In this case, it's a 60-40 coin. Okay? So this is our model. We have a model. Our hypothesis is either most coins, 99 out of 100, are good coins and they're 50-50s, and 1 out of 100 coins is a 60-40 coin. So we're going to flip a coin 50 times. We get 33 heads. We would expect 25 on average, but 33 ain't that far from 25. So is it a good coin or a 60-40 coin? Bayes to the rescue. So notation-wise, we're going to see B is a biased coin or a 60-40 coin, and F is the chance of seeing flips like this given whatever hypothesis we're testing. Okay, let's read it out. So the probability of a biased coin, our prior belief in how likely it is to get a 60-40 coin. This is the probability of the observed sequence of 33 heads given that it's a biased coin. We normalize by both possibilities. The possibility that it's biased, that's the same thing as what's in the numerator, right? And the probability that it's a fair coin. In this case, by the way, if you're not familiar, saying B with a hat or a line on top of it is the same thing as saying I would use this notation, but I copy-pasted this from somewhere else, right? Not B or not B or however you want to write it. That means not biased, okay? All right, so we can simply do the math. Probability of observing flips like this, anybody know the distribution? It's the distribution of a sequence of coin flips. Binomial. I heard at least one Bernoulli. Bernoulli is a single flip. Binomial is a sequence of flips. Okay? What does a binomial look like? Well, if you're not familiar, it's the number of heads to the power of how many of them? Sorry, my bad. Sorry, I just did this wrong. Somebody should tell me as soon as I start writing things. Da, da, da. It's the probability of heads raised to the number of heads. Probability of tails raised to the number of tails. And then in the front, it's the total number of flips. No. You guys should scream at me as soon as I do it. It's the number of heads, total number of flips. In a, oh God, is it a permutation or a combination? It's a combination, right? Combination. Okay. Whatever. You can go look it up. It's the binomial. That is what is going on right here. Okay? 50 flips. Oh, I did have it right the first time. 50 flips, 33 heads. The biased coin is 60% heads and 40% tails. Right? And then this is just the number of heads again and the number of tails over there. Okay, so that binomial fills up there. What's our prior belief in how frequently we get biased coins? Just 1 out of 100. Okay? And so that's it. That's the math, right? The denominator has got the same thing, but just with the probability of an unbiased coin being 99 out of 100 in our belief system. Do the math, turn the crank. We get an 8%-ish. Whoops, I went too far. Thank you, Wi-Fi. An 8%-ish chance of this coin being biased, right? A low percentage, but not negligible. Okay, this is on the slides. Don't freak out. You can review it. Okay, what if we're suspicious? Like 8% isn't nothing. I'm going to do more flips. I'm going to do experiment number 2. And I'm going to update my beliefs. So I start with my 8% as my new prior probability. And my new observed sequence of 50 flips is 29 heads. That's less than the 33 we were talking about previously. But it's still more than 25, which is what we expect. So the evidence is still trending towards biased. Now we run the numbers, the same binomial, just with the 29, right, instead of the 50. And we end up this time saying 46% chance that this coin is biased. We started with 8. We observed a sequence that wasn't even as bad as we had observed previously, but we're slowly updating our beliefs, accumulating evidence over time, becoming more and more sure that this is a biased coin. Make sense? Ish, conceptually? Okay, so what we're going to do next, I know I'm basically out of time, is we're going to look at another way in Friday's lecture that we can use this kind of math. Maybe you're familiar, right? We'll talk on Friday. Have fun, everybody. Oh, and enjoy your labs on Friday. You'll be going to them before you see me.